Okay, so welcome to this talk. I am Aneesh Ukidve. I'm in fourth year. I am going to be talking about how we define infinity. So, how many of you are first years? Show of hands. No. Okay. Okay. So you've seen some kind of set theory in your course. Have you? How much have you seen? Like, what have you seen? Anyone? What is set theory? It's not a trick question. Just tell me how much you know so that I can proceed. You know what a set is? Okay, very good. Good enough. Okay. So the objective of this talk is kind of twofold. One, obviously we want to see what infinity is and how it's defined and everything. But two, I want to stress the importance of set theory. So set theory forms the foundation of the mathematics that we do. And in some sense, everything in mathematics can be described by sets. So I want to, like, through this construction, we will see how everything is basically a set. Okay, so that's kind of going to be my objective. Right. Okay, how many of you know how to count? Yeah, 1, 2, 3. Wow. Okay, thank God. Okay, you guys know how to count, right? Okay, can you tell me how many circles there are on the board? 5. Okay, how do you know that? What do you mean you counted?
We start with 1 and then we increase.
You start with 1 and then you increase. Okay, sure. Anyone with a better answer? I mean, that was a correct answer. I'm just saying. You know there are 5. It's not a trick question. There are 5 circles. How do you know that? Bolo? You shut up. Maybe in your head, this is how the mental process might have looked like. You went, okay, this circle was 1, this circle is 2, this circle is 3, this is 4, and this is 5. And we've run out of circles, there must be 5 circles on the board. Right? Is that what you did?
Yeah.
Some variation of that? Okay. Okay, so what are we really doing? So if I wanted to count like this instead, so I call this circle 1, circle 2, circle 3, circle 4, circle 5, and circle 6. There are 6 circles on the board.
No, we consider each of them exactly once.
Exactly once? So every time I look at a circle, it should be labeled only once. Right? Okay, what about this method of counting? What if I did, okay, this is circle 1, this is circle 2, this is circle 3, this is circle 4. There are 4 circles on the board.
So we did not consider all the circles.
We didn't include all the circles, right? Okay. So what you want is that you're somehow labeling these circles in your head in a way that 2 labels don't go to the same circle and all the circles have labels in the end. Right? Is that a fair way to describe it?
Yes.
Okay. So you've seen set theory, you know what functions are.
Yeah.
So what I've described here, if you've been paying attention, is a bijection from this set to this set. Right?
Yeah.
Everyone knows what a bijection is?
Yeah.
So it's a one-to-one function that is also onto. All the elements are covered and no 2 things go to the same thing. Right? So in order to count, we need these labels. Right? So what is this set? 1, 2, 3, 4, 5. What is it made up of? Natural numbers? Right? So in order to count, we first need natural numbers. Right? Okay. So what are natural numbers? I'll just get rid of this for now. Okay, can anyone tell me what a natural number is?
It is used to tell how many things there are.
Sure, it is used for that, but what is it?
Number starting from 1.
Number starting from 1, okay, can you make it more precise? So 1, 1.5, 7, those are also numbers starting from 1. Okay. Have you seen something called piano axioms? In class, you must have seen. Can anyone tell me what the axioms are? I'll just quickly write them down.
There is the first number that is 1, and every number has a successor that is given by n plus 1.
Yeah, sorry. So the first axiom says that, okay, 1 is a natural number, but I'm going to start with 0. Okay, what's the second axiom?
Every number has a successor.
Right, so if n is natural, then n plus 1 is natural. And can you complete the rest? There are 5.
Induction वाला था mathematical induction.
Okay.
Zero
0
has no
has no.
there is no number that
Yeah.
is successor.
No,
So
0 is not the successor.
and finally, one more. Come on. Okay, the last one is that the successor function is injective. No two numbers have the same successor. Right? So I'll just write if n plus 1 is m plus 1, then n is n. But okay, sure. So in mathematics, this is how you define natural numbers. So these are a set of numbers such that 0 is there. If a natural number is there, then there is something called a successor. Okay, and this successor is unique. Right? Every number has a unique successor. So 0 is a natural number, and then uniquely there is another successor, and then a successor for that, and a successor for that, and it never loops back. 0 is not a successor, it never loops back. Okay, and the last one is the induction hypothesis, which is a clean way to say that these are all the natural numbers. There is no more. Okay, so induction hypothesis basically says that if a statement is true for n and you prove that it's true for n plus 1 and it's also true for 0, then it's true for all numbers. But a clean way to say that is that these are all the natural numbers. Okay, right. So any set that follows these properties we call natural numbers, and natural numbers follow these properties. But now, okay, these are very nice properties to have. But if I came up to you and I said, okay, I have this portion of immortality and it grants me everything in the world, what would you say to me?
Give me the portion.
Yeah, you need proof of this portion to exist, right? Okay, these are nice properties, but does there exist something that has these properties, or I'm just bluffing? I mean, for the first year here especially, it might seem a little odd that you have to prove that something that you know already exists. But this is how we do it in mathematics. So in mathematics, everything is defined in terms of sets. Okay? If you have a set which has these properties, then it is the natural numbers. Okay? So I must give you an explicit construction of a set which has these properties. Does that make sense? Or am I losing? No? Okay. So here is where something called von Neumann ordinals comes in. Name is scary, it's nothing scary. Okay. Von Neumann ordinals is basically an explicit construction of natural numbers. So I'm going to tell you how mathematicians essentially define natural numbers properly. So what we're going to say is R0 is going to be the empty set. Okay, everyone knows what an empty set is? It's the one set that has nothing. Okay, so 0 I'm going to define as the empty set. And then for a set A, I'm going to define A plus 1. This is going to be A union singleton A. Okay, looks weird currently, but once you see how the natural numbers look, it will make sense. So my natural numbers are going to be 0 and all of its successors like this. Okay, so okay, before going to the other axioms, let's see how these numbers look like. Okay, so 0 looks like phi. How does 1 look like? So 1 is 0 plus 1. How does it look like? So by definition it should be phi union singleton phi, right? And phi union anything is just that, because there is nothing in phi. So 1 looks like singleton phi, but instead of writing singleton phi, I'm just going to write 0. Okay, till here is fine. Okay, what does 2 look like? So 2 is the unique successor to 1. What is this by definition? 1 union singleton 1. So 1 union singleton 1. A union singleton A, the same set. Right, and if you open this, what was 1? It was the set that was 0. This was the set that was 1. So this becomes simple enough. So 2 is the set 0, 1. What would 3 look like? Yeah, 3 is 2 plus 1 is 2 union singleton 2, but that is exactly 0, 1 union 2. This is 0, 1, 2. And so there is some pattern. The set 2 has exactly 2 elements. The set 3 has exactly 3 elements. So you can see why this might become the natural numbers in some sense. Is that all right? Am I losing some of you? No. This is fine. Okay. So this is called, so these numbers, these 0, 1, 2, these are called ordinals. We'll come to why they're called ordinals, but essentially they form the set of natural numbers. Okay, and we have okay, so you can actually prove these properties. So 0 is not a successor. Let's say I need to show that 0 is not a successor for anything, right? So which means, to the contrary, if a plus 1 was 0, then what would happen? So A union singleton A would be empty. Is this possible? No, because A belongs to this set, right? In particular, A belongs to this set, right? So empty set cannot contain any element. So 0 is not the successor of any element. You can give a similar very short proof that if A plus 1 equal to B plus 1, then A has to be B. Do you want to try that? Okay, guide me through. I'll start writing. You can guide me. Okay, so suppose it happens that A plus 1 is B plus 1. What would that mean? A union singleton A is the same as B union singleton B. Okay, what's so wrong about that?
Sets are equal, that means their elements are equal.
Okay.
And they are the same number of elements.
Yeah. So you have A union singleton A equal to B union singleton B.
And A belongs to that one, B belongs to that.
Right.
B
So A belongs to this set. A in particular belongs to singleton A, therefore it belongs to the whole set. So A must belong to B union singleton B. Now if A belongs to singleton B, then A must be equal to B. Right? That is what it means to belong to singleton B. So on the contrary, we can assume that A doesn't belong to singleton B. So then we must have that A belongs to B. Assuming that A not B, we must have that A must belong to B. Now you can do the same thing the opposite way around. You can say, okay, B belongs to this set, so B must belong here. But B is not A, so B cannot belong here. So B must belong to A. So I must have that. So A belongs to B and B belongs to A. So in particular, set theory does not allow us to have sets like this. So there cannot be two sets that belong to each other. The axioms of set theory don't allow us to do that. Okay? So once we reach here, this is a contradiction. Okay, so what we assumed must be wrong. So A must be equal to B. So assuming that A plus 1 equal B plus 1, we get that A equal to B. That's fine? Okay. But, right. So, so finally, what we get is that this set 0, 1, 2, and so on, these actually form the natural numbers. And now we can go back to counting. So now if I want to say that there are 5 objects on the board, what will I say? Bolo, bolo.
Make a bijection from the subset of natural numbers to those.
Yeah, but there is a cleaner way to say that there are 5 objects on the board. Because of how we have defined them, the set 5 has exactly 5 elements. Right? So now we can just say an object, there are 5 objects because there is a bijection with the set 5. If you want me to remind you, this was the set 0, 1, 2, 3, 4. So there are n elements if there is a bijection with the set n. Right? A very nice way to count and precisely describe what counting is. Right? Okay. So, yeah. One of the cool things that we can do with these numbers as sets is that we can define an ordering on it. So, I'll just take away that part. Okay. What do I mean by an ordering? We can describe a relation where we can say something is less than another thing. Okay. How would you say 2 is less than 3? How would you define it?
Because we cannot make a bijection from the set 2 to set 3.
No, but you cannot make a bijection from set 3 to set 2 as well. So, yeah, subset is a good solution. But because of how we've defined it, A is less than B if A is a subset of B, but also if A is a subset of B, A belongs to B. 4 belongs to the set 5. So does 3. So does 2. So does 1. Everything less than 5 is inside 5. Essentially 5 is the exact set of all the things that are less than 5. Does this make sense? So essentially there is a very nice order, and this always holds. So 4 belongs to 5. So 4 belongs here, this element is here, but also this subset is exactly equal to 4. 0, 1, 2, 3 is exactly the set 4. So 4 is also a subset of 5. Right? And so we can describe this ordering on these numbers. And this ordering is a very nice kind of ordering. It's called a well order. Okay? You don't need to know precisely what it means right now, but it's a very strong form of ordering. It's a very nice ordering. So the property that a well order has is that if you pick any subset, there is always a least element. Okay? In this case, we can get the least element by taking the intersection of the entire thing. And then we get so if I have a subset of this, and as sets I take their intersection, then the only thing in the intersection is whatever belongs to all of them, right? Which by definition is the smallest. So this set is called a well-ordered set, and this ordering is where we get the name ordinals. So these are called von Neumann ordinals because they have a well ordering on them. Okay. So far so good. We have described a way to count objects that we know, and now we'll move further. Now we will move to the focus of why we are doing this. So what we want to get at is we want to in some way describe the size of sets. Okay, we want to say when a set is bigger than another set. Okay, and this ordering obviously is some way to say that something is bigger than, some set is bigger than another set, but we want a stronger notion. Okay, so essentially, okay, I forgot to tell you. So this is the natural numbers that you're well aware of, but when we are defining it as ordinals, we call this set omega. Okay, omega or omega 0 sometimes, but usually omega. This basically just means natural numbers. Okay, this is just notation. Okay, so what we want to do is, sorry. So up till now, whatever objects we defined, they were finite objects. Each set that we have defined up till now, so let's say 5, the set 5, it has exactly 5 elements. There is a finitely many elements there. And now the definition is a little circular. I say that a set has finite elements if it is in bijection with one of these. Would you agree? No, I've lost everyone. So when do you say a set is finite? What does it mean for a set to be finite or have finitely many objects? What is countable? We just learned how to count. Use it. Right, but instead of subset, you can just say there is a bijection from one of the ordinals into this set. So a set A is finite if it is in bijection with one of the ordinals n. Right? Does this make sense? Is this fine? Right? So if I have 5 circles, they are finite because they are in bijection with the set 5. Right? If I have 100 objects, they are in bijection with the set 100. Any finite set is in bijection with one of these ordinals. Okay? Okay. But now here's where it breaks. So this 0, 1, 2, blah, 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 all of these I put together in a set called omega, and omega is a set thanks to something called the axiom of infinity. Okay. Anyways, main point being omega is a set. Okay. Omega is the first such set that is not in bijection with any of these. Would you believe me if I said omega is not in bijection with 100? What about 101? For any finite number n, omega has more elements than n. There is no bijection from n to omega. Right? So omega is the first such example of an infinite set. Okay? This is called the first infinite ordinal, again represented by omega. There is also another name for it which we will get to later. It's called Aleph naught. But yeah, this is the first time that whatever we have constructed is not in bijection with any of the ordinals. Okay? This is the first infinity. Okay? Now, anything in bijection with omega is said to be countably infinite. Have you done this in your course? I don't know if you have. Not yet. Okay. The term is, so if anything is in bijection with this set omega, we say that that thing is countably infinite. It's infinite, but in some sense we can count it. We can go 0, 1, 2, 3 and so on. We can label each of the elements in such a way that all of the elements will be covered. Okay. So, okay. You guys know what integers are? Okay. Are there more integers or are there more natural numbers? More integers in what way? Are there more integers or are there more natural numbers? More integers in what way? Okay, so in one sense there are more integers than natural numbers because natural numbers are completely contained inside Z. Right? In some sense. But what I want to describe is, okay, so let me draw the integers. So 0, 1, 2, 3 and so on. And here we have -1, -2, -3, -4 and so on. Okay, so this is integers on a number line. Okay, now what I'll do is I'll start counting them. Okay, which means I'll start putting them in bijection with n. Okay, so I'll label this 0, then I'll label this 1, I'll label this 2, 3, 4, 5, 6 and so on. If I keep doing this, will I cover all the integers? Yes? And no label goes to the same thing? So there is a bijection from natural numbers to integers. Right? In some sense there are exactly as many integers as there are natural numbers. So this is why infinity is such an unintuitive concept, because even though natural numbers are completely inside integers, there are, you know that these things are not in the natural numbers. They're in some sense they are still the same number of integers. Okay. This property is called having the same cardinality. Okay. Two sets have the same cardinality if there is a bijection between them. Okay. So this the set of integers is countably infinite because it can be put in bijection with omega. Or another way to say is the set of integers Z has cardinality Aleph naught. This is just another way to say it. Right? Another question, are there more Rational numbers, or are there more natural numbers? Yeah. Rational numbers are also countably infinite, but you will see the proof of this later, hopefully. Okay. So, whatever I'm doing here, I am defining some kind of bijections, okay? So, what I want to eventually do is come up with a notion of how to define the size of two things. We know that if a set is finite, it can be put in bijection with one of these. If a set is countably infinite, it can be put in bijection with omega. I want to do this in general. Any set, I should be able to define some kind of size of it. Okay? That's what I'm trying to achieve. Okay. But before we do that, there is a small game. So, this is how we've defined the first infinity. And now what is going to follow is some of the most unserious piece of mathematics that I've ever seen. But this is, keep in mind, this is serious math done by serious mathematicians. Okay. So we have omega, right? We've defined this set omega. Now, there is nothing stopping me from defining omega plus 1. Right? I have omega. I can define omega plus 1. What is this? This is just 0, 1, 2, blah, blah, blah. And at the end, there is an omega. Right? No? So, this by definition should be omega union singleton omega. Right? So, omega is this set 0, 1, 2, 3, blah, blah, blah. Yeah, I mean, there is no omega minus 1. These are all the natural numbers. So 0, 1, 2, 3, blah, 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 all the natural numbers, and then another element called omega. Does this set make sense? There is nothing wrong, right? I've defined, for a set, I've defined what it means to do plus 1. Right? Maybe if you're more comfortable, I'll write it as omega 0, 1, 2, 3. Notice there is no number whose successor is omega. Okay. So omega is just something that is sitting after the natural numbers in some way. Okay. So I have this omega, and again notice that omega is less than omega plus 1. This is the title of the talk, infinity is less than infinity plus 1. Because of the ordering we have defined, omega belongs to this set. So it's just less than omega plus 1. But notice that if I label this as 0, if I label this as 1, if I label this as 2, and so on, what is this set? Omega. And what have I created? A bijection. There are as many elements in omega as there are in omega plus 1. And this is the first time this happens. For any finite ordinal, n plus 1 always has more elements than n. There is no bijection between the two. This is the first time that I have an ordinal, I have added 1, and I still have the same number of elements in some sense. Right? Which is why infinities are a little unintuitive. Right, okay. But if I have omega plus 1, I can make omega plus 2. What is that? It's just 0, 1, 2, all the way. Then omega plus 1. Right? If I have omega plus 2, what's the next step? 3. And so on. I can keep doing this. Well, if I have all of these, then I can create omega plus omega. And just to make these a little clearer, okay. So before writing this, I want to come back to how we created omega from 0, 1, 2, and so on. So we defined 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. And then we took the union of all of them and put them into one set. and this union we called omega. Okay, so when I'm saying if I can define omega plus 2, omega plus 3, omega plus 4, so on and so forth, I take the union of all of them and I get this new set omega plus omega. Okay, so a good way to visualize ordinals or like feel what I'm doing there is to look at the order of it. So ordinals are defined uniquely by their order. What I mean by this is, okay, so here is the set omega, okay, it looks like this 0, 1, 2, 3 and so on, right? Here is how the set omega plus 1 looks like. 1 less than 2 less than. Is this notation clear? What is what I'm trying to say clear? So it has all of these elements, right? 0, 1, 2, 3, and it also has an omega, right? And omega is bigger than all of them. Is diagram clear? Right? So omega plus 1 can be visualized as this diagram. Okay. How would omega plus 2 look like? 0 less than 1 less than 2 less than blah blah blah. All of them are less than omega, which in turn is less than omega plus 1. Right? Now if I add omega plus 3, there will be an omega plus 2 term here. Right? So how would omega plus omega look like? So 0, 1, 2, blah blah blah, all of them less than omega, which is less than omega plus 1, which is less than blah 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 blah. So there are two copies of the natural number that are placed right next to each other, right? And one of them is completely less than the other. Okay. So yeah. So this is how omega plus omega looks like. Okay. Yeah.
Omega plus 1.
This one. Okay. So we defined something called. Wait. Are you confused about what this set is, or are you confused about this notation?
This notation.
Okay. So omega plus 1 is the set that contains 0, 1, 2, 3 all the way till omega. Right? It contains all the finite numbers and also 1 omega. So omega plus 1 is this set, right? Yeah. There you go. 0, 1, 2, 3. And omega is just greater than all of them. Right? Okay. So omega plus omega looks like this. There is two copies of natural numbers placed right next to each other. And one of those copies is completely bigger than the first copy. Okay. And I'm going to define a notation for this. Instead of calling it omega plus omega, I'm going to call it 2 times omega. Well, if I have 2 times omega, I can write 2 times omega plus 1. I can keep doing this until I get 2 times omega plus omega. I can get 3 times omega. So, for visualization, this is how 3 times omega looks like. There is a copy 0, 1, 2. There is another copy omega plus 1, omega plus 2. And there is another copy 2 omega, 2 omega plus 1, and so on. There's like 3 copies of omega joined together. That's what 3 times omega looks like. And now you must have gotten this gist. If I have 3 times omega, I can create 4 times omega, and so on until I have omega times omega. You want to see how this looks like? Yeah, okay, I'll just take this away. I didn't leave enough place. Okay, omega times omega can be represented in this way. So in the first row, I have 0, 1, 2, 3, 4, and so on, all the finite ordinals. In the next row, I have omega, omega plus 1, omega plus 2, again, till whatever. Then here is 2 omega plus 1. So each row is less than the row after it. So anything here is less than everything here. Right? So this is how omega times omega looks like. And to be clear, omega times omega is the set that contains all of these. Right? It's the union of all of these. So omega times omega is this, like this diagram, or this whole set is omega times omega. Like I said, this is one of the most unserious pieces of mathematics because you can just keep going. There is no end to this. This omega times omega I'll define as a new notation. I'll call it omega square. And you can see what's about to happen. Right. So if I have omega square, then I have omega cube. Omega cube looks like an actual cube. You have this plane of omega, and then you have another plane and another plane and another plane and so on. Like this infinite plane. Omega 4 onwards we cannot visualize, unfortunately. It goes into the fourth dimension and I cannot think of the fourth dimension. Now if I have omega power whatever, I can go all the way to omega power omega. And I wish it stopped there, but if I can go to omega power omega, I can go here. If I can go there, well, and I can keep doing this, right? So this is something called a limit ordinal. So there are many omegas here in this power tower. Okay, this has a special name. It's called epsilon naught. Okay, epsilon naught is omega power omega power omega power. Notice that I gave a subscript 0. You know what's about to follow. So epsilon 1 is this. And so on. You can keep going. Then you get this tower of epsilons going the other direction, and so on and so forth. This is the most I mean, you gave mathematicians one toy, that is, you can add plus 1 and then you can take union. And this is what they've created. Okay. But the very remarkable thing about all of these sets, so these are unimaginably large sets, right? They're like omega cube tak we can imagine, kind of. Omega cube is this big infinite cube. How do you visualize omega power, omega power, omega power, omega power, whatever, and then it keeps on going. The remarkable thing about all of these is that all of the sets that I've written so far are all countable. All of them are in bijection with omega. None of them, they're not more, there are exactly as many elements in omega as there are in whatever this monstrosity is. Which is very, very, very funny to me. But regardless, if you keep doing this, and you can keep doing this infinitely many times, you can keep going and going, eventually, this is a very vague statement, eventually you hit a set which I'm going to call omega 1. So I keep following this process slowly, slowly, slowly. So I create this, then I do this plus 1, and I do this plus 2, and so on and so forth, until eventually I hit an ordinal which is not in bijection with omega. Okay. It is maybe slightly hard to believe that if everything is countable till now, that after some point it will not become countable suddenly. I know it might be hard to believe that, but I mean, you've already believed that a few minutes ago. When I said, okay, 0, 1, 2, 3, 4, all of them are finite. Why is their union suddenly infinite? Why does that size suddenly increase like crazy? Intuitively, you've already believed that, but there is a proof of this, but the proof of this will be a little technical. and I don't want to take a lot of time. But essentially what you can do is, okay, suppose all of these are countable. Okay, we take the union of all the countable orderings. Now that union is uncountable. There are uncountably many countable ordinals, right? And omega 1 is precisely the set that contains all the countable ordinals, right? Because anything that is less than omega 1, so if I say an ordinal is less than omega 1, what does it mean? Alpha belongs to that. So alpha is something that comes before omega 1. It is by definition a countable ordinal. So omega 1 is by definition the union of all the countable ordinals. And okay, so finally I will get to the crux of the matter. So you remember we said that, I'll take this away. You remember we said that omega has cardinality aleph naught. So these are called aleph numbers. Okay, so the first countable infinity. So these are the same sets. Okay, but we forget about the order. Okay, what I mean by that is a set A is said to have cardinality aleph naught if there is a bijection between aleph naught and A, right? Aleph naught being omega. Now that we have hit our next infinity, this is the first uncountable infinity, we will call it aleph 1. This is the first time an infinity is bigger than aleph naught. And there is nothing in between. This is the next infinity. This infinity is strictly bigger than this infinity. What do I mean by that? There is no bijection from the first infinity to the second. It is strictly much more massive. Right? In no way can you count the elements of aleph 1 using aleph naught. Okay? So this is where we have, and okay, once you get to omega 1, you can keep doing this process. Okay, you can keep, once you get omega 1, you can get omega 1 plus 1. And you do the same insanity, eventually you hit an ordinal called omega 2, which is the next infinity. Okay, which is the first infinity that is strictly bigger than omega 1. Is this believable or no? Have I lost you? So the same, so wherever we have done omega, we can just now write omega 1. And we keep doing this and we keep doing this. And then eventually, you look at all the ordinals that are in bijection with omega 1 and you take the union of all of them. And this is your omega 2, the next infinity, so to say. Yeah. Plus? No, not plus 1. So omega 1 plus 1 is in bijection with omega 1. Yeah, any of the previous one. Omega 2 is the first such thing that is not in bijection with anything less than it. Right? So yeah, that is the main property. These are called limit ordinals. They don't have a predecessor and they're not in bijection with anything that is less than it. Okay. I have to mention something. Sorry. What was I going to say? Oh yeah, okay. And okay, now that we have, so these are so a set can have size 0, 1, 2, 3, n, or aleph naught, aleph 1, aleph 2, blah blah blah. And again, these subscripts are ordered by natural numbers, which means these are ordered by ordinals. So there is again this notion of aleph omega and so on. It doesn't stop here. And we can do math with them. Okay. So Okay. How do you know this? I mean, there are multiple ways to define why this thing is, but one nice way to think of it is that I take the ordinal 2, 0, 1, and just for fun, I'm going to label it 0, 2, 1, 2. Okay, and I take another the ordinal 3, and I'm just going to write 0, 3, 1, 3, 2, 3. Now, in the union of them, the union of these is in bijection with 5. Right? So we say that our ordinal A plus ordinal B is some ordinal C if the disjoint union of A and B is in bijection with C. When I say disjoint, I mean that I'm like this 0 and this 0 are not the same. I'm separating them. Okay. And now with this definition, you can start to do math in the cardinal world. So, can you tell me what aleph naught plus aleph naught would be? Why? So what do I mean? Aleph naught plus aleph naught means I take the disjoint union of 2 copies of aleph naught and I see what it is in bijection with. Right? So 2 copies of omega we have already seen 2 times omega. That is again a countable ordinal, so it's in bijection with aleph naught. So this is again happens to be aleph naught. And particularly, actually this happens for any infinite ordinal, cardinals alpha and beta. Alpha plus beta is always equal to the maximum of alpha beta. You can prove it maybe, but it always happens that if you take the disjoint, because if alpha is, let's say, smaller than beta, then alpha plus beta cannot have more elements than beta plus beta, right? And beta plus beta is always in bijection with beta. Again, I'm saying these things in the air, but yeah, they need a proof. You can also multiply them and you get the same result. Alpha times beta means you take alpha many disjoint copies of beta and see what it's in bijection with. And it just so happens that for infinite ordinals, this always holds. There is one final operation that we don't do often. And okay, so the final operation that I'm going to describe, I'm also going to justify in some sense why an infinite ordinal that is not countable should exist. Okay, let's see what I want. So suppose A and B are sets. Suppose A and B are sets. Then we define another set called B power A. What is this set? This is all the functions from A to B. We are looking object, but this is just notation. So these are any functions from A to B. Those functions need not follow any properties. This is just notation for all the set of all functions. Okay. In particular, I want you to see what 2 power A is. So what is 2 power A by definition? Functions from A to 2, and 2 is the 2 element set 0, 1. Right. So for a particular function f, okay, some element A takes 0, some element B takes 1, or whatever. Right? They can take the values 0 and 1. If we collect all the elements that take value 1, so what am I saying? I'm saying, okay, so for given an f, I'm going to construct a subset of A. What elements are in C? All the elements of A that take the value 1 under F. Is this fine? Let's call it CF because it's coming from this function. Okay. So given a function, I can come up with a subset. Okay. If I give you a subset of A, okay, can you create a function from A to 0, 1? So what am I saying? I have a subset. I have a set A. I have some subset of A. Okay. I can define a new function. I'll call this FC. That takes FC of A is 1 if A is in C, 0 otherwise. Would you agree this is a valid function? So given a subset, this is called a characteristic function of C, but that's not important. So if A is in this set, I will give it value 1. If not, I will give it value 0. This is a function from A to 0, 1. Right? What I'm trying to say is that 2 power A is in bijection with the subsets of A. There are as many subsets of A as there are functions from A to 2. I think I've lost it. Yes? No? Yes? Okay. Because C of FC is C again. If you try to construct this subset from FC, then you get back C. If you try to create this function from CF, you get back F. It's a bijection. There are as many subsets in A as there are in as there are functions from A to 2. So 2 power A is also known as the power set of power set of A. Right, this is another notation for the power set of A. And Cantor proved that A can never be in bijection with 2 power A. The size of A is always strictly less than 2 power A. So in particular, we know that aleph naught is strictly less than 2 power aleph naught. Fine. So 2 power aleph naught is a cardinal which is not countable. So some ordinal, some cardinal exists that is definitely not countable. And maybe next semester you will see that 2 power aleph naught is exactly the size of the real line. Maybe next time, hopefully in real analysis you will have this. Oof, I'm taking up too much time. Yeah, okay. Does anyone have any questions? Yes, go. The functions one? Yeah. So what I'll do is I'll try to give a finite example and maybe that makes more sense. So I'll take A to be the 3 element set 1, 2, 3, 0, 1, 2. Okay. So 2 power A is all functions from 0, 1, 2 to 0, 1. Okay. Can you describe such a function? Any function? Can you describe any function from 0, 1, 2 to 0, 1? Just any function will do. What should I put as f of 0, let's say? Sure. F of 1? Sure. F of 2? Okay. Okay. Now, I'll take all the values that corresponded to 1. Okay, I'll collect all the elements such that f of A is 1. Which element should I take? Nothing. Right? So in this case, we are going to get the empty set. Right? This is a subset of A. Yeah. Okay. So I'm taking an example where a is just 0, 1, 2. 2 power a is by definition the set of all functions from 0, 1, 2 to 0, 1. Okay. So this is one such function. One particular function that they've chosen. So that is f of 0, f of 1, f of 2. All of them go to 0. Okay.
So we have chosen that they go to 0?
Yeah, it's just an example. Like, so suppose I am considering this function. Then what I'm saying is I construct this subset CF. This CF is constructed by taking all the A is that F of so in this case what would CF be? Empty. No element goes to 1. Right? So this is the empty set in this case. So given and okay, suppose I am given this empty set. So I start with a subset of A, suppose the empty set. Now I will construct a function which takes value 1 on exactly CF. Which is such function? Which is such a function? So there is only one function that takes value 1 nowhere. This one. The one that takes value 0 everywhere. Right? So I am defining a bijection between these functions and these subsets of A. For every function, look at where it's 1 and collect that into a subset. So let's say if I take another function, let's say f2, where f2 of 0 is let's say 1, f2 of 1 is let's say 0, and f2 of 2 is let's say 1. So again, this is a function from 0, 1, 2 to 0, 1. It takes value 1 on 0 and 2. Collect that and put it in into a subset, call it CF. So CF is 0, 2. So in this way, I can create all the subsets of A. For any subset, I can always create a function that takes value 1 exactly here and value 0 outside here of this. So there is a bijection between the set of functions from here to here and the number of subsets of A. No, am I losing? Is this clear? No. Right? So essentially 2 power A is essentially the power set of A. Power set of A is the set that contains all subsets of A. That I did not prove. This is thanks to something called Cantor's diagonalization. This you will see hopefully next sem. I don't know if you've seen it this sem, but you'll definitely be seeing it next sem. It comes thanks to Cantor's diagonalization, and for any set this holds. In particular, in your real analysis course, you will probably see this particular example, that Aleph naught is strictly less than 2 power Aleph naught, which is R. But yeah, that's it. Maybe we'll see. Yeah. Any other questions? No? Okay, then I'm done. Yeah, you can leave.